So you've probably been thinking to yourself, if we're estimating and trying to find out where mu is because we don't know mu is unknown, so we do a confidence interval, or maybe we don't know what pi is, capital Pi, we do not know what the population proportion is, it's some unknown value. So we're going to do like, p hat plus or minus z times pq over n for the proportion, square root. And for mean, we're going to do x bar plus or minus z times sigma over root n. And you're saying, well, if we don't know mu, how do we know sigma? And the answer is we don't always, and actually seldom do we. So then, how do we estimate sigma? What is sigma? Sigma is standard deviation of a population. If we don't have the population standard deviation, can we use the sample value to estimate it? And the answer is yes. So we use the sample standard deviation, S sub x, from our calculator oftentimes, but we use the sample standard deviation. So now we have x bar plus or minus something times s over root n. And what we find that since s is not as accurate as sigma, we can't actually use the z distribution because it's not an exact standard normal curve. So what happened is there was a guy named William Gossett. I think I have his first name right, but Gossett was his last name, and he did a lot of studying and investigating and found that there was a graph similar to a standard normal curve, but not a standard normal curve, but followed some normal tendencies, and it was called a t distribution. Now, he published it under the pseudonym Student, and the reason why is he actually worked for a beer company, and he figured if he did, no one would really value his insight into what was going on because they'd think, he wasn't a legit mathematician, even though he was. But what he found is that, let me draw a z curve. Let me just draw several here. So I have a normal curve that's kind of like that, okay? Really, really wide, a lot of area underneath the tails. That particular t will have a very low sample size. Let's say it's 4, all right? As n increases, the tail areas get less. And as n increases more, the tail areas get less. Ooh, that one should come down and underneath. And I ran out of room because of my all right. And what's happening is as n gets larger, the t distribution approaches a z distribution. And this is why at the bottom of the t distribution, at the bottom of every column, it says confidence level, and it's, if it says 95%, you look at that one number right above it, and it's for infinity n. So when n is super, super, super large, my t is essentially a z. All right, so since it's a slightly different distribution depending on the sample size, I've got this table of values that's different for everything. So go ahead and look at your t distribution. So go ahead and find it either in the back of the book or you have your you have this with you, and we look at the t, the one that says t, and across the top of the t, first it has a picture at the top that's kind of like this, with this area shaded, all right? And then across the top, it has tail probabilities, 0.25, 0.20, the smallest one they go is 0.0005, okay? I'm going to write one here in the middle of 0.025. Okay, so there's different ones. And then underneath it, there's these columns of numbers. And then over here it says df. df is words for degrees of freedom. df is equal to n minus 1. So if I do a sample of, let's say, size, we do a sample of size 10, all right, I have a df of 9, because that's n minus 1. If I look across the 0.025 column down to 9 degrees of freedom is 2.262. 2.262. How am I going to use that? Here's how you're going to use that. When we're doing a problem such as a confidence interval, and I have x bar plus or minus t times s over root n. All right, 0.025. If this is 0.025, that means the other tail, although not shaded in the picture, is also 0.025, grand total of 5%. That means that's in the 95% confidence interval column. If you look to the very bottom of 0.025, it says 95%. So in a 95% confidence interval, this is the number that I use right there. Okay. If you remember, in a z distribution, it was 1.96, a smaller number because it's closer to the mean, because remember, as n approaches infinity, that t distribution gets narrower and narrower and taller until it approaches a standard normal. And again, remember, standard normal means a z distribution. Z is standard normal curve. All right. So that's how we're going to use this distribution. It's just another type of normal-ish curve that we use when we don't know sigma. So that gets us back to, with those conditions, the last condition that I typically have you do is after simple random sample and after independence and after normality, we have sigma. Is sigma known? All right, and this is only for x bar. Okay, when we're ever using p hat as an estimate, it's still SRS, it's still independent. So again, the rule for independence is my population over 10 times my sample size. If this is true, if there's independence, then we know sigma sub p hat is equal to pq over n square rooted. So in a proportion problem, if our conditions, if these three conditions are met, so this is the independence, and then normality, normality being NP greater than or equal to 10, and Q greater than or equal to 10. All right, so if simple random sample, independence, and normality are all met, then I will always use Z. I will never do T for a p hat scenario. I will only use Z for p hat. So over here, it's only for x bar that I could potentially use Z or T. Simple random sample, if it says it, we say that it is. We check and we actually show the work for population over 10 times the sample size. Normality, either the population is normal or n is at least 30, and that's because of the central limit theorem. Or my normal probability plot is approximately linear, which we haven't created one yet, but we'll do one soon. Those are the three ways to show normality of a sampling distribution of x bar. Normality of a sampling distribution of x bar. All right. So then at the end I go, do I know sigma? If I know sigma, then I use Z. If I do not know sigma, that's when I use the T distribution. All right. This is why it's so important to do these conditions, because at the end of this one you're going to say either, therefore use Z, or you're going to say therefore use T. All right. And that's what we're going to do as we approach the next step in our process of doing confidence intervals. All right. So let's see. For a reflection response, I need you to go into, so the T distribution is what's called robust, R-O-B-U-S-T, robust. All right. Robust is very significant with the T distribution. I want you to go read the definition and come up with your own understanding of what robust is when it comes to a T distribution. So if you didn't bring your book home, you're going to have to look it up online. But again, if you look up T distribution robust, something should come up. And I want you to read what that is, try to figure out what that is, and then make sense of it and explain it in the reflection response. All right, so that's the idea of robust. So that's your job. Watch the video, fill out the reflection response for everything else. Make sure you're asking me good questions, always asking me good questions about this content, not just about life in general. And then come to class and I'll see you then.